Start recording. Oh, all right. So, we are now at a point where half the class has dropped and you're the only one remaining. I'm just kidding you, just looking at the. All right, so let me share something with you. I do not mean to scare people, but it is fact, okay? It's factual. When I took assembly language programming at San Francisco State University, it was taught as a once per week class. So on Monday in the evening, the class would start at 7 p.m. and it would end at about 10 p.m. in San Francisco. So I would take the bus, to get home at about 10 p.m. And back then it was safe. I was never concerned about, issues with crime and whatnot. But the funny thing is the class started off with 60 students. So it's a pretty big class, kind of like two of these classes combined and then plus some. And there were about 12 people left at the end of the semester. So the 20% of the students, original students, remained in the class. Now it's tough because it was taught on a VAX machine. It was made by Digital Equipment Corporation, which then later got bought by Compaq of all companies. And there were only 4 dumb terminals on the entire campus that can be used to do the homework for that class. So can you imagine, meeting only once per week for 3 hours in the evening on a Monday? You have only 4 computers or 4 terminals, dumb terminals that could be used to do all the homework assignment. And the professor who taught this class also taught at UC Berkeley, and he would bring in concepts like page faults, virtual memory virtual memory management and stuff like that. So those are much more advanced concepts in operating systems. In other words, he moved way beyond assembly language programming or computer organization. So I think that was my second computer class, second computer science class, and it was good. I really enjoyed it. Learned a lot of new things.
What year was that?
That was 1986. Yes, yeah. Back in those times, most computers or most programming classes need to use mainframe or some kind of centralized computer, and there's no such thing as dial-in, not even modems. You really have to be on campus in the computer lab because the dumb terminals were hardwired to the mainframe computers. Yep. All right, so what we're going to do today is we are finally starting to get into assembly language programming. And as I said, this is week 10, and this is where we are at this point for this class. So what I'll do is I'm going to demonstrate how to use the processor and also a little bit of how to use the tool, because this is going to be the lab for you today. So I want you to be kind of prepared for the lab, but also understand the concepts. That is, the concepts are kind of like the theoretical portion. This is kind of like the practical portion of how to use the processor. All right, so I know some of you would be very tempted to follow along with everything that I do. You can do that, but I would not recommend it because everything is being recorded right now as I speak. So I would just kind of focus on the concepts and ask questions. When you say, okay, I'm not really quite seeing how this connects to that, okay, because that's really important, is to ask questions. All right, so let me get started with the command line because I want to show you how to start running the program. So I got everything downloaded already. The instruction of how to do this is actually included in the lab, so there's no need to kind of frantically try to copy everything that I do here. So I got everything downloaded to CISP310 in a subfolder called processor. So these are the 4 files that you need. According to Walter, who is one of the technicians maintaining the computers here, they got OpenJDK already installed on these computers, so you probably should be able to run Java today. So I'm going to start this up, java-r jar logisim, and then processor 0004.circ. You probably don't need to do it like this because on the Windows machine, you can just double click on the jar file and then you can load processor 0004, revision 4, just by opening that from within logisim. So this is the processor. One of the suggestions that I have is to print this out, okay? Print it out either as a PDF, you can do it electronically, or you can do it on pieces of paper. Whatever you do is up to you, because some people are more comfortable with physical paper so they can highlight. Other people are more electronic, because you can also highlight if you have a PDF and you have the right tool on an iPad or something like that to do the highlighting. So whatever you do is up to you. However, I do recommend that you take not a screenshot, because when you go to logisim, you can actually print it. So you can print the main circuit. And typically, I would just use the printer view, and then you can set up what printer to print to. On my computer, there's a PDF output. I think most Windows systems and Mac OS also has something similar. So you'll be generating a PDF, then you can just highlight and mark up the PDF in different ways. So I'm just doing that as a recommendation. So in this class, okay, in the other class, I talked about the add instruction. So you're more than welcome to check out the video recording from other classes, not just from this semester, okay? If you say, I want to see what you're going to talk about in 2 weeks from now, you can actually go check out all the video recording from past years and get a sense of where this class is going, okay? So that's all available. But as far as we are concerned, let me just kind of write down what I want to do. So I want to go to mousepad, and I'm going to open up a new file. I can actually just reuse this. So what I want to do is to say I want register, let's say D, to be storing the D minus register B. So I'm referring to registers. Register D needs to store the difference between register D and register B. Okay, so the first thing is, what registers are we talking about? Did I talk about the register bank in this class? I don't think so, right? Okay, so we'll start with that, okay? So the first question is, where are the registers? So the answer to that question is they're all in the register bank. So from the perspective, yes, go ahead.
Where do we find that?
Hmm?
Is the file posted for this?
Yes. In the lab today, it will contain instructions so that you can actually download it. If I want to show you, let me show you where you can find it, because some people may want to do that. So if you go all the way back to the first module, it has a shared folder. Oh, okay, never mind. Try again. There we go. So you go to the shared folder. Once you get to the shared folder, you go to processor. And then once you get to processor, there are 3 files that you need to download. So once again, I would not suggest that you guys do it now. But these are the 3 files that you need to download in order to get the processor to work in logisim, in addition to logisim310.jar. Is that okay? Yeah, the instructions are all in the lab instructions for today. So I'm just basically performing all of those steps. Kind of behind the scene, I have all of these files downloaded. Just like in infomercials, they will have all of these pots with food that is already cooked before the show. They will show like 20 instant pots, and they all have something going, right? So kind of the same deal. All right, so this is the register bank, okay? And the register bank contains the registers that your instructions can specify and access explicitly, okay? There are many other registers within the processor, but from the software perspective, they are just kind of in the background. You do not have direct access to those. But there are 4 registers inside the register bank that you have direct access to. So to look into a component and see what it has at this point, you do a right click on the component and then you say view register bank. So the register bank shows the 4 registers: register A, register B, register C, and register D. So those are the 4 registers. So what I want the processor to do is to subtract the value of register B from the value of register D and then store the difference back into register D. That is what I want it to do. Is that okay? So I'm going to put some values here because subtracting 0 from 0 is not very fun. So what I want to do is to specify this is the subtrahend, so I'm going to specify a large value, something like 9b, and then in the minuend, I'm just going to store something that's smaller, let's say 21 in hexadecimal. So in this case, I'll be subtracting 9b in hexadecimal from 21 in hexadecimal. Is that okay? All right. So these 4 registers are software accessible, which means you can write instructions to specifically say, I want to subtract register B from register D. So the next question is, don't we need a subtractor to do the subtracting now that we know who is supplying the subtrahend and who's supplying the minuend? So that's why we need to go find the ALU. This is the ALU, which stands for Arithmetic and Logic Unit. So all computations are done by the ALU. So that includes addition, subtraction, comparison, right shift, bitwise not, bitwise and bitwise or. So all of those operations actually doing the computation, they're all done using the ALU. Do we have any questions at this point? Right shift means you are shifting all the bits or the binary digits to the right-hand side. So everything gets to move one place to the right-hand side except for the rightmost bit, which basically just disappears. And then from the left-hand side, we shift a 0 in. So basically, you have a 0 shifting in from the far left, and then the bit all the way to the far right will be shifted out of the value. All right, so let's go ahead and take a look at the ALU, which is not simple because the ALU is actually somewhat complex as its own thing. But I want to direct your attention to the components that are actually doing all the hard work. So this is an adder, this is a subtractor, and so on. How do I know this is an adder, other than there's a plus sign on it? On the screen right now, where do you see the word? Yep.
It says CN for carry.
CN for carry, but there's something even more direct. Yes.
In the description, it says add.
Yes. So when you select a component, it says, this is what I do. I add, right? So you can now click on the other one. This is a subtractor. This is a shifter, and it's performing right shift. It's a logical right shift, but we'll get to that when we need to get to that. This is bitwise not. This is bitwise and then this is bitwise or. So all these 6 operations define all the basic computation that this processor can do. Not a whole lot, right? You don't see sine or cosine. You don't see multiplication. You don't see division. Well, that's because in a real processor, those other things can also be done in software. Okay? If you tell me that you already know how to do subtraction, you know how to do compare, I can do division. If you say I can add, I can shift, and I can already do, I can do multiplication. So all of the other operations can be done, can be boiled down to these 6 operations. And not even all 6 are required. It's just handy to have these 6. So right now we want to do a subtraction. So that means somehow I need to get the values of register B and register D into the input of the subtractors, right? So this is where the poking tool is going to be helpful because you can also kind of hover over. This is the minuend. So that means which register should be connected to here eventually. So from the description, okay, let me switch back to the description here. Which one is the minuend? Register D, thank you, thank you. So register D is indeed the minuend, so that means I need this wire somehow to be connected to the minuend. But wait, hold on a second here. This wire goes into a demultiplexer. This is a demultiplexer. So somehow I need the input of the demultiplexer to connect to this specific output of the demultiplexer. How should I configure the select, which is here, so that output 1 connects to the input for this demultiplexer? Yes?
It should be 0, 1, correct?
You're correct. It's 0, 0, 1 in this case because there are 8 possible outputs, so the select has 3 bits. But you are correct. It is 0, 1. But to name all 3 bits for the select, it's 0, 0, 1. Very good. All right. And at the same time, I also need this particular demultiplexer to be enabled. Okay. Right now it is disabled, but I need it to be enabled. So this way, in 1, coming from here, will connect to out 1, which then connects to the minuend input of the subtractor. What about the subtrahend, which is this connection here? Well, let's see. This one connects to the second demultiplexer, and you can see how this is also output 1 of the second demultiplexer. So basically, I can use exactly the same select, which is the whole point of the select bit, to the demultiplexers on the left-hand side and also to the multiplexer that is on the right-hand side. They're all synchronized. Okay? They're all basically saying we all want the second thing, okay, which is the subtractor. Okay? So the inputs are controlled or routed by the demultiplexers. Then the output of the subtractor is routed by the multiplexer so that it becomes the output. But you can see, we also want to connect input 1 to the output for the multiplexer. And once again, they all connect to the same select bit. Are we doing okay so far? So the select bits are basically synchronizing the 2 demultiplexers and the 1 multiplexer. So we can now say, okay, which thing in between do we want to actually do the calculation? Are we good so far? All right. So what we have worked out at this point is simply to get the content to the right input pins. So these two are the input pins. So now the question is, but how do we get the registers to these input pins? Are we doing okay so far with this? All right. So now we go back to main, and then the input pins are these 2 respectively. And somehow I need to get the resistors, not resistors, but the registers out of the register bank. So now we need to take a second look at the register bank, and then we ask, we need this to go to in 2 because it's supposed to be the subtrahend, and we need this to go to in 1 because this is supposed to be the minuend. Is that correct? Well, but first of all, we have to configure the multiplexers first, right? In other words, it's not getting out unless the multiplexer says, yeah, okay, I want you to be the output of this multiplexer. Is that okay? So let's check out, let's go back outside again. This is going to be, this is going to be our minuend, which means this wire needs to eventually connect to register D, because that's our minuend. So you basically say, how can this wire eventually connect to one of the outputs of the register bank? And you can say the only thing that is in this way to connect to some output of the register bank is the demultiplexer here. So somehow I need this wire to connect to this wire here. This is the output of the demultiplexer. I need it to connect to this input of the demultiplexer. Does that make sense so far? So now the question is, I do apologize for the distraction. This is for the design hub, because I have a Discord running. So how do we get this done? How do we connect this input to this output here? This is, by the way, output 1. So what do I need to do? I need this select here to be 0, 1 to select output 1. And I also need register output 0 enable, which is the name of this tunnel, to be a 1 to enable the demultiplexer. Is that okay so far? What about the subtrahend? The subtrahend is into. So the subtrahend is a little bit more convoluted because the first thing is we need to configure this multiplexer so that it would select not input 1 but input 0 to connect to the output. So this is the select pin. I know it looks really kind of awkward, but I ran out of space for the design, so it's touching the actual select bit here. So I need FC to be a 0 in this case. FC is this particular tunnel. It is the NAND between register output 1 demux and ALUEN. If I need FC to be a 0, I need both of these inputs to be 1s. ALUEN has to be 1, and that kind of makes sense because we need to enable the ALU if I want the ALU to do something. But this is register output 1 demultiplexer. I need that to be a 1 as well. So if you look at this wire, okay, so we can see how that is connected to here, because if I want this wire to eventually to connect to this wire, that means this wire in between needs to connect the output of this multiplexer to this input of the multiplexer. So that means this multiplexer needs to have a select of 1, right? Which matches what we need here because this needs to be a 1 in order for FC to be a 0. Are we doing okay so far? I know I'm spewing out a lot of blah, 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 blah like that, but eventually it depends on how we want to route the registers to things that are actually doing something. So that means, so I just answered a few questions already. I need FC to have both inputs being 1, which means ALU enable has to be a 1, and ALUEN, by the way, is also found here. We also need register output 1 demux to be a 1, and that turns out to be here, and that also configures the demultiplexer the way that I need it to be configured. So now I have found routing. In other words, I have found a way to route output 0 from the register bank to the minuend. I have found a way to route output 1 to into, which is our subtrahend. And we also know this is supposed to be register D because register D is the minuend, and this is supposed to be register B because register B is supposed to be the subtrahend. So now we look back into the register bank and we ask, we need this to hook up to this over here. So the question is, how do we get it done? How do we get the Q port of register B to become register output 1 of the register bank? What is standing in the way? There's only one component standing in the way. It is it's a mux, it's a multiplexer, okay? So the only thing standing in the way is a multiplexer. So we need to connect input 1 of the multiplexer to the output of the multiplexer. This multiplexer is always enabled, so we don't have it enabled to deal with here. So the question is, how do we configure register output 1 select? How should we configure these 2 bits over here? 0, 1, very good. Okay, so that we solved one mystery. And now we need to look at register output 0. This needs to connect to register D over here. So once again, what is in the way is a multiplexer, another multiplexer. So the question now is, how do we configure the select of this particular multiplexer so that it connects register D to register output 0? And this is the wire that we need. Yep, go ahead.
0, 4? Oh, no. 1, 1.
1, 1 is correct, okay? Very good. Okay, it's 1, 1, even though it's the 4th input, but since we count from 0, it is 3, and 3 in binary is 1, 1. All right, cool. So we have just figured out all those bits, right? To make the connectivity to connect the registers to the subtractor. So the next question is, when the subtractor is done doing the subtracting, I needed to store back into register D, right? So here's register D. We need to somehow say, register D, I want you to be prepared to be updated. So how do we do that? Well, I think we need the enable to be a 1. And this enable is connected to the decoder here. So that means, how do we need to configure the decoder in order for register D's enable to be a 1? I need this wire to be a 1. This is a decoder, which is kind of like a demultiplexer, but with a constant of 1 as its input. So the question is, yes?
You just need to designate which pin to use on that. That reg in selector needs to be 1, 1.
That needs to be 1, 1. Very good. And I also need a 1 here to enable the decoder. That is correct. So now we have actually figured out every single bit that we need to get this whole thing to work, okay? So let me summarize, okay? It's going to be a little problem, it's going to be a little bit headache-ish, because what we need is okay, oh, wait, I haven't finished the entire story, because this is where the difference is, okay? This wire over here is where the difference is. So I need that difference to be going into the input of the register bank. So that means I also need to first enable this multiplexer, and at the same time, I need to make sure that it is selecting input 1 to connect to the output over here. Is that okay? I can't turn off Discord because one of the students is actually attending remotely, so I can't turn off Discord for now. I can probably turn off the notification of the channel that I'm on. So let me do that. Right click. Yeah, so I'm going to mute it for, I'll do it for 3 hours. So I think we should be good for now. All right. So I think we got everything figured out. I need RIMux to be a 1. I need RIEN, which enables both this multiplexer and the decoder inside the register bank at the same time. I need RISEL to be 1, 1, so that the register to be updated is register D. I need RO0 cell, which is register output 0 select, to be 1, 1, because it is supplying the minuend. I need register output 1 select to be 0, 1, because it is supplying the subtrahend, which is from register B. I need register output demux to be a 1, because that is how we can connect output 0, which is the minuend, all the way to input 1 of the ALU. I need register output 1 demux to be also a 1, because that is how I connect the subtrahend through this demultiplexer, to become the subtrahend going into the subtractor. I need this operation select for the ALU to be 0, 0, 1, because that's how I route both inputs and the output to the second thing that does any operation within the ALU. Let's see what else. I think I got most of it. ALUEN has to be a 1. All right, so the begging question right now is, Tag, are you really going to go manually, click on all of those things and set up all the bits?
Oh, isn't it like what you were saying about the Thomas the Train track engine? It's
Yep.
like a diagram for
Yep.
each thing, so if we need
Yep.
a specific thing.
So the question is, who is going to change all of these bits, right? Because we got one bit over here, RISE. There are 2 bits with RISEL because it's selecting one of the registers. 1 bit over here, 1 bit over here, 1 bit over here, 2 bits over here, another bit over here, another bit with ALUEN, which is here, and then 3 bits over here. So the question is, who is going to do all that? I mean, I'm not going to click, all day long. Remember, the whole thing is we want everything to be contained, and I don't need to do manual reconnecting and connecting. So if you track down these tunnels, I know there are a lot of these tunnels, but if you track down all the tunnels, they're all here. Look at, this is register input enable, this is register input select, register output 0 enable, register output 0 select, blah, 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 and so on. And you can see how all of these are going into a splitter or merger because of the direction. And that all go to microcode data. And a microcode data is just one of the many things coming out of the ROM. So the ROM component is basically how everything is orchestrated. So the ROM, each location of the ROM component has a lot of bits, okay? 1 bit goes here, 2 bits go over here, 3 bits go over there, another one goes over here. So they all control the routing between the components of the processor. Is that okay? Cool. All right. But then the next question is, who gets to decide which location of the ROM is spewing out all of these content to get things done? That becomes the next question, right? So the location of the ROM is determined by the microcode pointer. So the microcode pointer, which is this component here, is directly driving the address port of this ROM, which means it's dictating which location of ROM the output is corresponding to. So if you do a right click and then do an edit contents, let me move the other window over here just so that you have a view of the content of the ROM. So you can see the ROM has some locations have non-zeros. It has mostly zeros because I overestimated how much space I need to specify all the operations. So a lot of space turned out to be wasted. But there are, a bunch of non-zero locations here. So this is what the ROM does. Okay, each one of these locations specifies 26 bits. Okay, 26 zeros and ones. The 26 zeros and ones, they all go to the enable and also the select of your multiplexers, your demultiplexers, your decoders. Some go directly into the enable of some of the registers. Some would go to the RAM component, like the select of the RAM component, the load pin of the RAM component, and so on. This is how the Sir Topham Hatt from Thomas the Tank Engine is orchestrating the connectivity between the rails. Okay, so this station now has a connection to that station over there. This mill now has a connection to the port over here, and so on. Is that okay? So every single location in ROM is one page of instruction that Sir Topham Hatt is going to use, and you basically have a panel and go like, okay, this rail, this switch over here needs to configure like this. This switch over here needs to be configured like this. Oh, by the way, this train should stop here, okay, and so on and so forth. Is that okay? All right. So now the question is, so what do we do, okay, as a person writing the program? What do we do to specify the operation that we want it to perform? So let me try to answer the question. So the key is to look into what we call the opcode table. So the opcode table is going to be one of the most important document here. I use a spreadsheet only because it's just a table, okay? So there's no actual code of any kind with this table. So we're going to start with looking for the right role to specify a subtraction operation. So let me first describe what each column is representing. Column C is going to be the one that we need to pay attention right now, because we want to match column C, or whatever each row has, to the operation that we are trying to perform, which is register D gets the difference between register D and register B. This is what we want to do. Okay, these are, so X and Y are placeholders. Each one, X can be A, B, C, or D. Y also can be A, B, C, or D. So let me just get to the right page, and then you guys can tell me which one we want to use. Yeah, it's somewhere around here. So tell me which row is going to resemble what we want to do. Now remember, X is a placeholder for register, Y is also a placeholder for register.
Row 25, column C.
Okay, so let's take a look at row 25. I'm going to highlight the entire row. And this is row 25. And the answer is yes, this is what we want to do. So if this is what we want to do, what is X going to be? In other words, X is a placeholder, but in this very specific operation that we want to perform, who is going to be register X? Register D, and that makes Y to be register B. Very good. Okay, so we are starting to work out all this stuff here. So we need register X to be D. We want register Y to be register B. Okay. So now that we are done with column C, because column C is what we call the register transfer language. It is one way to describe a very atomic operation that the processor can perform. Okay, which means it cannot be divided into smaller operations. So column C is super helpful because it describes to us what each instruction or what each opcode is trying to do. Column D is probably pretty easy to read as well because it's just the English word describing what it is. So we are trying to subtract, right? And this is the subtraction in C syntax. So now we are left with column A and column B. Column B is what we call mnemonic. Okay, these are the mnemonics of opcodes. Why? Because do you want to memorize column A instead of column B? Now I know column B doesn't look like English, right? Using sub instead of subtract. Right shift is RSH. JC is jump if and only if carry is 1. Okay, so it is kind of cryptic, right? But it still beats the other version, which is all zeros and ones, right? So can anyone guess what the processor reads instead?
Processor reads A, correct?
Yep, exactly. So the processor reads column A. Column A is what we call the opcode in zeros and ones. Those are the exact zeros and ones that we need to tell the processor, hey, I want to perform this operation over here. So we're going to focus on row 25, and the opcode has this particular pattern, which is 1001, which means 1001 has to be there. It has to be the most significant 4 bits of the opcode. But then the X and the Ys are now in XXYY. XX is basically the 2 bits that we need to say, oh, register X is represented by these 2 bits, and YY is for Y. So can someone tell me what XX should be in this case and what YY should be in this case? So I'm going to pop this up so that you guys can see that register X is register D. So XX, which is the 2 bits to designate register D within the register bank, what should that be as base 2, in base 2?
No, because if it goes up to D, we're talking about hexadecimal, correct?
No, this is in binary.
Binary?
Yeah, so each lowercase x here is 1 single bit, which is a binary digit. So if you remember in the register bank, we got register A, register B, register C, and register D, and we count in that order as well. So register D is corresponding to 3, and in binary it is 1, 1. Very good. Okay, so we now know that XX needs to be 1, 1. And what about YY? Which is the 2-bit representing register B. 0, 1. Very good. Okay, so I think we are getting it. So now the opcode is going to be 1001, which has to be there. And then the XX has to be 1, 1. The YY has to be 0, 1. So the question is, would you rather remember the bit pattern of 1001, 1101, or would you rather say this is SUB, which is subtract, and DB? Yeah, but the zeros and ones are easy. I mean, there are 26 letters in the English alphabet, but there are only zeros and ones for the other one.
So
But we are not wired to deal with a bunch of zeros and ones. We are more wired to go like, at least SUB resembles subtract, right? I mean, that's the mnemonic. All right. So in the other class, I actually got into the discussion of why the mnemonics are so short. Okay, why don't we spell it out? I mean, it's not like the typing is going to kill the time. It's not going to waste a lot of time. So the short answer to that question is, well, if you're typing, it doesn't take that much more time. But if I want you to use punch cards, punching that extra hole or punching those extra holes to specify a longer mnemonic instruction, that does take a lot more time. So that is why the mnemonics of these operations tend to be really short. It's not because we cannot type fast. It's because in the good old days, the programs were written and in punch cards. And you don't want to punch unnecessary holes unless you really have to, because one row of a punch card is one character. So you have to find the right place and go like, yep, J, M, P. Okay, so if you say J, U, M, P, you have to punch one more row, which means you have one more chance of making a mistake. So that is why all of these mnemonics tend to be really short, because in the good old days, people do not like to punch unnecessary holes on the punch card. Are we good so far? All right. Cool. Okay, so that means we should be ready to run the instruction. So now I go back to LogicSim, and I'm going to use the word inject, in this term here. So I'm going to inject, the code that we just figured out, but that was in binary. Let me go back to here. This is in binary. The RAM component wants you to enter the content in hexadecimal. So the question is, what is 1001, 1101 look like as a hexadecimal number? So first of all, we chop it in, groups of 4. Go ahead. Oh, you're just working? Oh, okay, I see. So what is the hexadecimal of 1001? We got 11, no 2, no 4, 18. It's 9. So does 9 have a hexadecimal digit?
It does.
Yes, because it's, in base 10 we have a digit, in base 16 it has a digit as well. Okay, so the opcode starts with a 9 in hexadecimal. So the next one is 1101, which is 9 plus 4, because we got the same 2 ones, but we got an extra one here. This is the 1 of 4. So what is 9 plus 4? 13, and what hexadecimal digits represents 13? Close. D is correct. Okay, very good. So D is the one that we want. Cool. So now we have figured out the opcode in hexadecimal. So this way I can quote unquote inject it into the processor and say, that's what I want to do. Okay?
9D, that's it.
9D, that is correct.
That's all you have to tell the processor, and then it operates that.
Yep. Don't you want to know how?
Yes.
Because that's what we're going to do next. All right. I mean, I cannot miss the whole opportunity of showing you how the processor works. Remember, this is one of those transparent V8 engine, the model thingy, where there's a tiny little crankshaft. You can turn the whole thing. You can start to see the valves moving, how the camshaft works, how the cylinder goes up and down, and so on and so forth. That is what I'm doing here. Okay? All right. So shall we start the execution of the processor?
Yeah.
Okay? So what you need to do after the lecture is kind of go back to the lecture itself, the video recording, and then you need to kind of write down, in your own words, okay, with screenshots if you want to, how the whole thing operates. Because right now, which is the time is 11:16. This is the beginning of the demonstration of how the processor gets things done, okay? So the first thing we want to do is we know everything is dictated by the ROM. So that means the first place we need to look is the ROM component. Once we get to the ROM component, the next question is, who is telling us where to look in the ROM and what is the content at that location? Is that okay? So I am reasoning this entire thing out because I know everything that the other parts of the processor does depends on how these bits are arranged. So that means the ROM, the content of ROM that is being output to its D port, dictates where, what is being done. Okay. So now we look at the A port. The A port connects to the microcode pointer. The microcode pointer is reset to 0, just like all the other registers, and that's why it starts off with 0, 0, 0, because I just started the whole logisim thing. The enable is always enabled, so that means this register never gets disabled. All right, so that's all we need to know right now. It is 0, and then location 0 has these particular bits. So the next portion is to look at the rest of the processor and then to ask exactly what is going on here. Okay, so there are a few things that you can write down, if you want to know the process of analyzing how the processor gets things done. There are only a few things that can actually do something, even though this picture is really, really busy. I can point out all the things that are actually important right now. All right, looks like the other student is not online. Okay, well, that's okay. All right, so we look at all the components and then we ask whether each one is actually being used or not. So let's look at the RAM component here. Does it look like the RAM component is important for what we're doing right now? And how do we know?
Because we have a 9D in the first or 0 slot.
Well, that's what we put into it, right? But how do we know RAM is being utilized or not?
I thought, well, don't we need it to
We do, but looking at the picture right now, the select is a 1. Very good. Okay. So the select of RAM is a 1, which means the ROM is telling RAM and say, hey, wake up, I need you to do something, right? So this is the kind of reasoning that I do, like all day long. It's a very simple thing. You know one thing, and then you ask additional questions related to the answer of the first question. So we just answered the question of whether RAM is being used or not, and the answer is yes. Okay? ROM just told RAM to say, hey, wake up, I need you to do something. What would be the natural next question?
what are we doing with it?
What are we doing? Exactly. So what can RAM do? There are two things it can do. One is I can give you the current content at this location, or two, I can change the content of a location. In other words, we can read from RAM or we can write to RAM. Which one are we trying to do right now? Which port dictates that, and what does it look like at this point?
We need to read.
Okay, go ahead.
Yeah, we need to read. And,
We are reading. How do we know?
because we are trying to get the instruction. Oh, the load circuit.
Because load is a 1, okay? Because load is a 1, we are specifying a read operation. Okay, so we just answered two questions, right? RAM is being used because we need to read it. The next question is, where are we reading it? Who's telling us where to read, and who is getting the content at that location? So those are the two additional questions. Are you guys getting the way I ask these questions? Okay? Because that is transferable from this class to just about anything that you have to reason out. Okay, you answer one question, you see that that thing is being used. How is it being used? Who is dictating which location, and who's using the content that is the output? So all of these questions, if you cannot track those questions, write it down on a piece of paper or use Notepad, okay? Because each one needs to be answered. All right? So now we take a look at the A port, and then we ask, we know what A port is, okay? Because that's easy to answer. It is just location 000. If you use the poking tool, that's easy to see. So that is not the question. The question is not which location are we reading. Instead, it is who is telling me to read location 0. Is that okay? Because those two questions are different. The first question is, what is A port? What is the value of A port? You just poke the Y, it will tell you right away. The second question is, okay, but it has to come from somewhere. who is telling me to read from location 0. So that's a more involved question because we need to now track it down. Okay, so we can track down the wire to this particular multiplexer. So from the picture, just from visually, can you tell which input of this multiplexer is connected to the output? So let me highlight the multiplexer. Come on, can I? Nope. Okay, I need to change back to the select tool. So if you look at this multiplexer, how do we know which input connects to the output? Every single multiplexer has a select, right? In order to tell it which input connects to the output. So just from looking at the diagram, do we know which input connects to the output? Yes.
Is it the adder multiplexer? The adder that's coming
The adder.
it says ADDR.
That's the select because it's under the gray dot. So this is light green, right? So what is light green representing and what is dark green representing?
Positive, negative, 1, 0.
Light green is 1, dark green is 0. Very good. Okay, so from what it looks like right now, this is light green, which means the select is a 1, which means which input connects to the output. This has to do with the behavior of a multiplexer. The second one, correct, input 1. All right, so this is input 1. So now we track down who connects to input 1 of this multiplexer. So now we have to scroll a little bit more, and we get to PC. So PC stands for program counter, okay? It stands for program counter. The program counter has one job, which is to tell the processor what is the location of RAM that contains the next opcode. That's its only job. It is basically Sir Topham Hatt's bookmark of which page am I on. Is that okay? So that means if you want to change the flow of a program, you change the program counter. If you want to move on to the next opcode, you increment the program counter. Is that okay? So the program counter is really just a little bookmark to say, okay, I'm on this page. I need to kind of track, okay, should I flip to the next page? Or is this telling me to go to a very specific page, in the book? Okay, that's the job of the program counter. Is that okay? All right. So now we answered most of the questions related to RAM, except for one, the last one, which is, okay, so now we know that program counter is specifying location 0 because that is where we want to get the opcode. But who's getting the opcode? Now we need to track down the D wire, okay, or the D port and see who is updating based on the D port of RAM. So once again, there are a few things, only a few things that can change. And in this case, we can kind of track down everywhere the wire goes to. Look at this demultiplexer. It's turned off. Okay, so it's not colliding with the D port. Okay, and you look at this particular multiplexer. The multiplexer itself is disabled. You can see how RIEN is dark green. So this multiplexer is disabled, which means this connection is not doing us anything. It's not doing us any good. You look down here. We have this multiplexer. This multiplexer has an input of 0, which means this particular input is not connected to the output anyway, so it's not a big deal. And then finally, you look at this connection all the way to the instruction register. So the instruction register is enabled. Okay, see this EN here? It is enabled. So that means on the rising edge, the instruction register is going to get the content at location 0 of RAM. Okay, let me just pause here and make sure that everybody understands what I said. The instruction register on the rising edge, okay, the instruction register is getting the content of RAM that the program counter is pointing to. In other words, if I were to use the register transfer language, this is what we are doing right now. We are saying the instruction register, I'm just going to abbreviate it to IR, is getting whatever the program counter is pointing to in RAM. In other words, I'm using the asterisk, the reference operator from C. Is that okay? Now, this is very important because this is the step where the processor goes to RAM and say, okay, so what am I supposed to do next? It's trying to get the instruction so that it knows how to get it done. Okay, what to get done, it's trying to get it. So this is important because this is the decode cycle when you execute any instruction. So I see not too many people writing anything down right now, and that's okay. But eventually, you probably need to write down in your notes, okay? This is known as not decode, I just took, excuse me. I was wrong, this is called a fetch cycle. The decode cycle comes like 2 steps later. This is called a fetch cycle. We are using the program counter to point to a location in RAM, and then we are asking what is at that location. That content in return goes to the instruction register, which is then remembering, okay, now I remember the opcode. And it will do something about the opcode in just a little bit. Are we good so far? All right. So now let's take a look at the rising edge. Okay, Control T will give you a rising edge. So if you go to simulate and we just want to take ones, that's Control T as a hotkey. It's really handy for what we are doing right now. So I want you to focus the attention to the instruction register. The clock is low right now. All registers would update on the rising edge except for one. But this is one of those where it will update on the rising edge. So I just type Control T on the keyboard, and you can see how the instruction register is now updated to 9D. This is the fetch cycle, okay, which is the first cycle of executing any instruction in the processor. And if anyone is thinking, oh, that's only for TTP, right? You'd be, nope. This is universal, okay? It doesn't matter which processor you're talking about. When you execute an instruction, it always starts with a fetch cycle, which is going to memory, grab the opcode, and put it somewhere within the processor. All right? Okay. So now we're going to have a falling edge, right? So the falling edge is meaningless to most components in the processor except for one. This one here is the only register that is configured to update on a falling edge. And it's for a good reason, okay? So this will update right now. So the question is, how is it going to be updated, right? So once again, I'm trying to use one question, the answer to one question to lead to additional questions, right? Because the one thing that I know right now, the starting point is the microcode pointer updates on the falling edge. And we are about to cause a falling edge. If I type Control T again, clock is going to go from high to low, which means we're going to have a falling edge. So the follow-up question is, we know the microcode pointer is going to be updated. So the follow-up question is, how is it going to be updated? Who is supplying the value to update the microcode pointer? And how do we know that? How do we track it down? Who is supplying the value to update the microcode pointer? Where do we start? Which port of a register is responsible to get the content to update the register itself? We got port D, we got port Q, we got EN, we got the clock, we got the clear or 0. Which one is responsible to specify the content? Yep.
Port D.
Port D, very good. Okay, so we know this is the one, so we now track down this wire. Well, it didn't go too far, did it? So what is the first thing that it runs into? A multiplexer. So when it runs into a multiplexer, what question would you ask? It has multiple inputs and one single output. We know where the output is going.
So what input is
Exactly. So what input connects to the output? From the diagram, just visually, can you tell which input connects to the output? Yes?
the selector is on, so we know that it's coming from point 1, correct?
Yep. It is not on, it is a 1.
Oh,
Yep. the device is always on because I need to be more specific about the term. It's always enabled because you don't see an enable pin by itself, so it's always enabled. But you're correct. The select is a 1, which means input 1 connects to the output, right? So now we track down input 1 of the multiplexer, and where is it coming from?
The adder.
It's coming from the adder. So that means all we are trying to do with the falling edge is we're just incrementing the microcode pointer. Because the adder has one of these input coming from the output of the microcode pointer, which is 0, 0, 0, right? And it has a carry in of 1. And then the other number that we're adding is basically 0, 0, 0. So effectively, we're just adding 1 to whatever the input is. So if I were to touch this wire, which is what I'm doing right now, it's 0, 0, 1. So it's just incrementing. Is that okay? So this particular step has no particular name because we are just moving to the next location, not of RAM, but of ROM. Okay? Because we are done with this step already. It's time to move on to the next slice of ROM. So Control T, not too exciting, right? Because we already knew the microcode pointer would update to 0, 0, 1. So the next edge is going to be a rising edge. So once again, we have to ask the question, what are we going to do with this rising edge? Registers and RAM are pretty much the only thing that will do something on the rising edge. So we just have to track down who is going to do something. And even from this picture at this point, you can barely see someone's EN is a 1. Just barely. And on the north side of what is displayed right now, do you guys see one of the registers has an EN being light green? The program counter. The program counter has its input being enabled. So once again, if it's going to be updated, the next question is, who is supplying the value to update the register with? Okay, so that becomes a follow-up question. So just from visually looking at this, okay, can someone tell me how the program counter is going to be updated? Yep.
It's going to be updated by the multiplexer, which in this case is a 0 for the selector.
Uh-huh.
So the 0 port is connected to the adder,
Uh-huh.
which is adding some stuff.
Which is adding a 1 to its input, and its input is the program counter itself. So once again, we are seeing an increment mechanism, okay? So on the rising edge, the program counter would increment by 1. Why? Because I'm done with location 0, 0. I just put the content of location 0, 0 into my instruction register, which means I don't really need the program counter to keep pointing to location 0, 0. I'm preparing the program counter to go for the next opcode. That's why we are auto-incrementing the program counter. So this step, once again, has no particular name because it really, it's just one of the steps that we have to do, which is auto-incrementing the program counter. So here's Control T, and the program counter becomes 0, 1. Are we good so far? So it's going to be a falling edge next, right? So what do we need to analyze on a falling edge? There's only one register that updates on the falling edge, and that is, go ahead. The microcode pointer, yes. So the microcode pointer is the only one that updates on the falling edge. So now we need to figure out how it is going to be updated. All right, so you guys can tell me how the microcode pointer is going to be updated this time. Everything that you need to know is already on the projector, so we just have to kind of figure that out one step by step. We know it's going to be updated next because this is on the falling edge. Clock is high right now. Control T is going to give me a falling edge. This is the only register that responds to a falling edge, so we know this is going to be updated. So the next question is, who is supplying the value to update the microcode pointer? We track it backwards to the multiplexer, right? The multiplexer has 0 as its select, so that means this time we're not incrementing, and instead we're using the input 0 of the multiplexer to update the microcode pointer. So now we need to go further back and say, oh, this is a splitter. So the splitter is basically a merger in this case, because bit 0 to bit 3, I know it's hard for you guys to read, but it says 0 to 3 here. So the bit 0 to 3 is a constant of 0. So they're already determined, okay? It's just 0, 0, 0, 0, 4 zeros. Bit 4 to bit 11 hooks up to a tunnel called instruction. Is that okay? But where is instruction coming from? I'm too short to point out by my own finger, so I'm going to use my virtual finger to point here. So it's coming from the tunnel, which is the output of the instruction register. And what is the content of the instruction register? 9B. And where did it come from again? Location 0 of RAM, okay? So this cycle is important. This is called decoding, okay? So in this particular architecture, the decoding is done by the microcode pointer. Microcode pointer is getting whatever the instruction register has, but we are also doing a left shift by 4. All right, so what do you mean by left shift by 4? We're shifting in 4 bits on the right-hand side. That's basically what it means. So let me just do a Control T, and now you can see what I mean by that. Look at the content of the instruction register. It's just 9D, but when you look at the content of the microcode pointer, it is 9D 0. That's the effect of left shifting by 4 bits. But if anyone is complaining, go like, Tech, you said 4 bits, but I only see 1 0. Well, because that 1 0 is in which base? In hexadecimal. And how many bits is 1 in 1 hexadecimal digit? Exactly 4. So that's why. But the effect of the ROM is, oh, look at this. We just went to location 9D0, right? And 9D0 is like, well, how did we get there? Well, we got there because the opcode is 9D. We attach 1 extra 0 on the right-hand side. It becomes 9D0. So that is why we are going to location 9D0. And this step is called decoding. So the last one is called fetching. This one is called decoding. In other words, I'm looking at the opcode. It's like, exactly how do I get it done? Now the ROM content being addressed is telling me exactly what we need to do. So now we go up to the other parts of the processor, and then we ask, alrighty, look at that. Who is active right now? So you can develop a list of things to check. So I tend to check the RAM first. Are we using RAM this time? Nope, RAM is not being used because it is not even being selected. This whole thing is just ignoring everything that's going on right now, okay? So we're not using RAM. What are we using? Well, you look at all the enables that are ones, okay, because that would be a good clue. And you look at the ALU. Oh, okay, so we have the ALU being enabled. And then we got a bunch of stuff enabled here. Register output 0 enable, okay. Register output 1 demux is a 1. That's not an enable, but nonetheless, it is not a 0. Register input enable, that's enabled. All right, so that seems to suggest that we are using the register bank because we are using the ALU. So now we need to ask, what are we doing with the ALU? So ALU OP is 001. Do you guys remember? We have the adder being operation 0. The subtractor is operation 1. That is what it is, okay? It's operation 1, which means we're telling the subtractor, we're telling the ALU to perform a subtraction. Is that okay? So the next question now is, where are we getting the minuend and where are we getting the subtrahend? So let's look at the minuend first. It's coming out of the demultiplexer. The demultiplexer is enabled, and the select, if you look at the select, is 0, 1. So that means the input, which is here, is indeed connecting to in 1 of the ALU. So now we have a path connecting the output, one of the outputs of the register bank, to the first input of the ALU. We'll address the other question of which register is being selected. We'll address that later. Then we ask the other question, which is, where's my subtrahend? The subtrahend connects to the multiplexer here. This multiplexer has a 0 as its input, which means input 0 of the multiplexer connects to the output, so we need to track down that wire. And that turns out to be the output, output 1 of this demultiplexer. This output 1 of the demultiplexer is currently connected to the input because the select of this demultiplexer is a 1. So now we also know that out 1 of the register bank connects to in2 of the ALU. Are we okay so far? So now we look into the register bank and say, okay, so who is output 0 and who's output 1? So we look into here, and we can see register output 0 select is 1, 1, which means this input of the multiplexer connects to the output, and we can see how this is coming from register D. So we know register D is being used as the minuend of the subtraction. We look at output 1, and then we try to track down who is supplying the input to specify as register output 1. That's determined by output 1 select, which is a 0, 1. So that means this particular input is being connected to the output, and that is coming from the output of register C. No. It has to be this one, sorry. This is input 0, 1. The other one is input 1, 0. This is input 0, 1, which is coming from register B. So we now know that register B connects to register output 1 of the register bank, which then in return connects to input 2 of the ALU in order to serve as the subtrahend. Is that okay? I know there's a lot of tedium to this whole thing, but this is how we track down all the details, okay? All right, well, we know a subtraction has a result. So the question is, who's getting the result? So the output of the ALU connects all the way to this particular multiplexer. The multiplexer is enabled, okay? This is the enable, it is enabled. And RI mux is a 1, which means this input indeed is connected to the output. So now we go back into the register bank and ask, who is updating because of reg in, because of this pin here? Well, tracking down this wire doesn't really help because it connects to the D port of every single register. But we can track down the decoder because the decoder will only output a 1 to one of its outputs, right? The select is 1, 1, which means output 3 of the decoder is a 1, which we can see by the light green wire. And it goes all the way to register D. So register D is also going to store the result of the subtraction. Is that analysis okay? I mean, I'm not asking you to memorize all the details of what I just said because that would not be possible. But I'm asking you, do you follow the way I reasoned out this entire thing? All right, so that's good because that is the important part because you probably want to do that to some of the other instructions or just repeat the experiment with this one and do something like this. So now we are going to perform the subtraction, which is 2, 1 minus 9b, and then store that result back into register B. So the question is, can you do this by hand? We got a 2, 1 minus a 9b in base 16. And it's the same thing, okay? Do you guys still remember multi-digit subtraction, the R thing, the B thing, and all that stuff, right? So we have a default borrow of T0 being 0. And now what is 1 minus B in hexadecimal? First question is 1 less than B?
Yes.
So that means we need to borrow, right? So right away we know that we need to borrow here. So now we have 1, 1 minus B in hexadecimal. What would that be? What is 1, 1 minus B in hexadecimal?
0.
Nope. 1 in hexadecimal is representing which quantity, which value? Nope. You talk about the result of the subtraction? Well, that might be, but I'm asking what is 1 in hexadecimal? 17, because 1 means I have 1 of 16 to the power of 0 plus 1 of 16 to the power of 1. So that means we have 1 plus 16, which is 17. What is B? B is 1 right after A. A is 10, so B is 11. So now we have 17 minus 11, which is a 6. So that means that we have a 6 here. Oh, I just totally messed up because I did not have a space here. So this is a 6. 6 minus 0 is obviously just a 6. Okay. What about this part over here? What is 2 minus 9 in hexadecimal? Well, 2 is less than 9, which means we need to borrow. So that means this is a 1 here. So now we have 1, 2 in hexadecimal minus 9. 1, 2 in hexadecimal is 18. 18 minus 9 is 9. So we have a 9 here. 9 minus 1 is easy. That's just an 8. So we're expected to see an 8, 6 being stored in register D. And we are also expecting someone to say, hey, there's a borrow here. Does that make sense? Maybe, kind of? All right, okay, cool. So what we'll do is we are going to perform the operation, Control T, right? So I want you to focus on register D and see if it is updating to 8, 6. Ta-da! Cool, right? But where's the borrow bit, right? Do you guys still remember, all the time that we spent to talk about binary comparison and there's a borrow and the borrow is really important? So who's tracking the borrow? So the borrow is actually, we can still see it in the ALU. We can see how the borrow out is here, but it's its own tunnel, and it is feeding into this multiplexer. This multiplexer still has 1, 1, 1 as its selector, so C out is also getting a 1, and then C out is combined with all the other bits to become the flag output, and then the flag output, now you don't have to deal with this for now because the flag output is going into the flags register, and that's why the flags register is getting the carry bit getting a 1, which is bit 0. All right, so we can kind of ignore that last part for now, okay? All right, so in order to do your lab, okay, this is not what your lab is asking you to do. Nonetheless, you want to do this to some of the other operations. So for this class, I would suggest that you try to find out and double check how to perform, let's say, this operation. Okay, so you might want to write it down as something that you want to do, but so replicating what I did today with subtraction, you want to do this with addition and figure out the entire thing. Single clock, Control T through the entire thing. Make sure you understand how things are connected. All right? So related to the lab today, what are we doing today? Well, let's get back to how we figure out everything here. We started off with what we want to do, and then we figure out which bits are representing D, which bits are representing B, and then we look up the opcode table, find out this is the bit pattern, and then we get back here, and then we figure out the least significant 4 bits are supposed to be 1, 1, 0, 1, and then the most significant bits need to be 1, 1, 0, 0, 1, anyway. And if I say you're going to write a program of, let's just say 60 bytes, and this is the way you're going to write it, what would be your reaction?
How much points is it worth?
You'll be going like this, right? So we need a better tool to do this, okay? So the better tool to do this is called an assembler, okay? So the assembler is going to be your best friend, even though you may not think so, for the rest of the semester. So the assembler is a spreadsheet, also in the folder of processor. So you just double click on the spreadsheet and you go like, how can the spreadsheet do anything, right? Well, this is a special one. So what you do is you go to the source tab, and I'm going to delete everything that I have here because that's from a program that I did way before. This is where you can write your program. Now, if you say, I don't want to write a program in the spreadsheet, that's okay. You can just use a text editor like this. And I'm just going to specify a few instructions here. The first one is double checking that we did not make a mistake. So we are subtracting B from D, like so. And the second one is something else. Okay. Let's say add, and we are adding register to register A, which is doubling register A. Okay, so let's just say that these are the two instructions that we want to do. Oh, we'll add the next one here, which is halt. What do you think the instruction halt is going to do?
Quits code.
It just halts. There's no way to quit. The problem is there's no way to quit because when you say, return 0 from main in a C program, it exits back to the command line or it exits back to the IDE because there's something else starting the execution of the program being debugged, right? But in this case, this is bare metal. There's no operating system. There's no command line, interface. There's nothing, right? So you have nowhere to, quote unquote, go back to when you're all done. So the halt instruction is the only way you can specify, hey, processor, we're good now. Just don't go anywhere. Because you don't want it to do any further computation that you do not intend it to do. So you just say, stay put, we're good. That's what the halt instruction does. All right, so let's just say that these are the three instructions that we want the processor to do. So what you do is you copy and paste, okay? Just copy this from a text editor and then paste it into the spreadsheet. Now, when you paste into the spreadsheet, do not paste when the cursor is blinking. That would not be good. So you want to make sure that the cursor is not blinking, then you paste, and you want each line of your code to use one cell. All right, so this is important. And then what you get in return is there's an assemble view, the assemble tab. Don't mind about the complex, formula up there. So what this is telling you is for the three instructions that we have, sub dB translates to 9D in hexadecimal. All right, so I did the hand assembling correctly, right? This is a good check. 80 is representing the add AA instruction, and then 01 is representing the halt instruction. In other words, all the trouble that I went through to hand determine all the zeros and ones, could have used the assembler to do it. Okay? But there's another thing that's important about this view, and somebody's going to ask me a question related to that. Column W is telling you the address of the byte that is stored in column X. Now, some instructions is going to take up 2 bytes. So let me go to source. I know I'm going a little bit over time, but I'm going to save you time in the end. So I'm not going to talk about the LDI instruction, just what it does. I'm not going to tell you, because it's not important, and neither is the no-op instruction. But what I do want to show you is what the assembler view is showing at this point. Do you guys see how it is skipping 04? Why is that?
Because, as you said, it takes up 2 bytes.
Exactly. So if I ask, what is the content of location 04, what would that be? I can tell you column X is the first byte corresponding to that line of code. Column Y is corresponding to optionally the second byte of that opcode. So knowing that, what would be the content at location 04? Yep.
I'm going to guess 60.
No. Okay, column X is the first byte corresponding to the instruction of that row. Column Y is the second byte corresponding to the instruction of the same row. Now, some instructions only has 1 byte, so they don't have a second byte, but LDI has 2 bytes.
I was just guessing because of the RAM, how it's set up. in that space next to it?
Not quite. So the way we do the counting is location 0 has a content of 90, location 01 has a content of 80, location 2 has a content of 01, location 03 has a content of 60, location 05 has a content of 00. So where is this guy? 04. Yep. So this is corresponding to location 04. Is that okay?
04 where?
In RAM. But that's a good question. I'll follow up with that question, okay? So we are looking at what we want to be in RAM, right? But RAM is here. How do we get that stuff in the spreadsheet into RAM over here? So I'm going to show you how to do that, okay? Because one of the questions will ask you to do the same thing.
So the first location is the number we want?
Hmm?
The 90 is the
So in this particular code, this 90 should go to this 90 here. So we got the first instruction already in here. So one way to copy the content from the spreadsheet to the RAM component of Logisim is to do it by hand. How many people really loves to enter hexadecimal digits? Yeah, I'm dying to do this, right? No, nobody wants to do that. So instead of doing that, which doesn't mean that you cannot do it, if you want to do it that way, that's fine. However, if you look at the tabs or if you look at the sheet name, one of them is called RAM file. So this one is special because what you do, you go to File within Google Sheets, and I'll just say this one time. Do not try to download the spreadsheet as an Excel file, period. Okay? Well, okay, I should say you can download it, but it won't work. It will only work as a Google Sheet. Okay? So go to File, and then what you do is you go to Download as a CSV. But you have to be in the RAM file tab. So it will give you some funky name. I configure my browser not to save as the name that is suggested by the server. So I'll just say this one is test.csv. And then you click Save. And the next thing is you go to Logisim, right-click on the RAM component, and which option do you think I'm going to use next?
Edit contents?
Hmm?
Edit contents?
Well, edit content is good for hand entering stuff, but I'm not going to do that. So which other one do you think is going to do what I want to do?
Load image?
Load image, exactly. So when you go to load image, it will ask you where the image is located. And of course, I cannot remember where I put it. So I'm going to say maybe it's in TEM, it's called test.csv. It's just a guess. Click open. Yep, that turned out to be right. So now you can see the content of the, oops, not this. Okay, where is it? Now you can see this content here being loaded into RAM. Is that okay? So one last trick before I let you guys loose to do the lab. How do I run this? Because one of the questions will ask you, run this code and tell me what is the content of register blah when it's all done. So how do you run it? You can do Control T, but Control T is going to you need a lot of Control T's, okay, especially if the code has a loop. So what you do is you go to Simulate, and then you want to do the text enabled, but before you enable it, you want to check out the frequency. Because right now the frequency is at 1 Hertz, which means you can type Control T faster than the auto clock, which kind of defeats the whole purpose of auto clock, right? So what you can do, if you want to still see some animation, and you can probably go for 16 Hertz or 32. So I'm going to go for 16 Hertz, and then you go to Simulate, and then you can click Enable Text Enabled, or Control K would do the same thing. All right, so well, I just executed one instruction, but it's okay. I can still do this. So we go to Text Enabled, and now it is all done. How do we know it's all done? There are two things you can use to tell that this is all done. The first thing is you look at the program counter. Do you see the program counter auto-incrementing and changing? Nope. So that means it's probably in a halt instruction, but it may not be, okay? Because if you have a jump instruction back to its original location, so I'm going to give you the most definitive way to tell whether your program has concluded or not. Down here, there's a pin called, output pin called halt. If the halt pin is a 1, that means your program has concluded. It cannot continue anywhere anymore. Is that okay? So I think with all of this, you are now ready to do the lab for today. So I'm going to stop the clocking. Control T is going to stop the clocking. And let me switch back to, okay, I don't even know where the, start a new tab here. All right, so we are now all the way down here with von Neumann architecture and memory. And we are doing the second to the last lab here. You cannot see it yet. I have not made it visible yet. All right. So does it have a passcode? Nope, this one actually does not have a passcode. I'm going to change the due date to 1:30. Is the Computer Science Club meeting today?
Yes.
Okay. I need to ask because we will have people waiting outside, hopefully. All right, so save and publish. There we go. So you guys can get started now. And so for those of you who are kind of thinking, what do you mean by computer club? So the Computer Science Club was started by, 3 of our own classmates in this class. Okay, we see some, I'm seeing some finger pointing. But anyway, Chris, basically rebooted the Computer Science Club, and it's meeting right after the lab of this class. So if you want to check out what they have planned to, for us to do in the club, just kind of stay after the lab or come back at 1:30, and then Chris will tell us what the plans are. In this classroom, right here. Yep. All right, so let me stop the recording and get the upload.